In 1343, a French physician named Henri de Mondeville wrote a prescription that would baffle modern doctors: 7 types of bread, each to be consumed at different times of day for different ailments. Dark rye bread in the morning to strengthen the blood, barley bread at midday for cooling the liver, wheat bread in the evening to settle the humors. His patients didn't eat bread despite their illnesses. They ate bread as their medicine. Fast forward to today, and bread has become nutritional enemy number 1. Gluten sensitivity affects an estimated 20% of the population. Celiac disease diagnoses have quadrupled since the 1950s. Diabetes and obesity researchers point to refined flour as a primary culprit. The wheat plant itself, Triticum aestivum, hasn't fundamentally changed its genetic structure in 700 years. So what transformed humanity's staff of life into something millions of people now avoid entirely? Medieval wheat wasn't a single variety, but hundreds of regional land races, genetically diverse populations adapted to local conditions over centuries. A farmer in Kent grew wheat different from his counterpart in Provence, who grew something different from a farmer in Bavaria. These weren't named, trademarked varieties bred for specific traits. They were evolutionary populations, each kernel slightly different from its neighbor, carrying genetic variations that provided resilience against disease, weather, and pests. The most common medieval varieties were Emmer and Einkorn, ancient wheats that modern botanists classify as covered wheats, because the grain remains enclosed in tough husks after threshing. These wheats contain 14 to 28 chromosomes compared to modern bred wheat's 42. The genetic complexity sounds like an advantage for modern wheat, but the additional chromosomes came from deliberate hybridization to increase yield and gluten content, not nutrition or digestibility. Emmer and Einkorn have simpler gluten structures with different protein ratios than modern wheat. They contain higher percentages of albumins and globulins, easily digestible proteins, and lower percentages of gliadins and glutenins, the gluten proteins that trigger immune responses in sensitive individuals. Medieval wheat grew tall, sometimes 5 feet high, with small seed heads containing 20 to 30 grains. Modern dwarf wheat, developed in the 1960s through the Green Revolution, stands less than 2 feet tall with dense heads carrying 60 to 100 grains. This dramatic yield increase came with biochemical changes. The dwarf gene that reduces stalk height also affects the plant's production of secondary metabolites, compounds that have no direct role in plant growth but interact with human digestion and metabolism. Research at Washington State University comparing Einkorn to modern wheat found that Einkorn triggers significantly less inflammatory response in human intestinal cells. The study, published in 2014, showed that while modern wheat activated inflammatory pathways in cell cultures, Einkorn did not, despite containing gluten. The difference isn't the presence or absence of gluten, but its molecular structure and the presence of other compounds that either facilitate or hinder digestion. Medieval farmers saved seed from their own harvests year after year. This practice maintained genetic diversity within their wheat populations. Each harvest naturally selected for plants that survived that year's particular combination of weather, disease, and soil conditions. Over generations, this created wheat populations uniquely adapted to specific microclimates: the chalky soils of Champagne, the heavy clays of Flanders, the thin mountain soils of the Alps. Modern wheat cultivation uses genetically uniform seeds, often hybrid varieties that don't breed true in the second generation, forcing farmers to purchase new seed annually. This uniformity maximizes predictable yields but eliminates the genetic diversity that provided nutritional variation. The timing of harvest mattered more than modern practices suggest. Medieval farmers harvested grain when fully ripe, sometimes waiting until the stalks had begun to dry in the field. This allowed complete nutrient development in the grain and began the process of enzyme deactivation that would continue during storage. Modern wheat is often harvested slightly underripe to prevent shattering during mechanical combining, then dried artificially to prevent spoilage. Grain harvested before complete maturity has different enzyme profiles and higher levels of certain proteins that some researchers believe contribute to digestive difficulties. Step into a medieval mill, either water-powered or wind-powered, and you'd find massive circular stones, each weighing up to a ton, grinding slowly at 15 to 20 revolutions per minute. The bottom stone, called the bed stone, remained stationary. The top stone, the runner stone, rotated, crushing grain between the two surfaces. The process was slow, taking several passes to reduce whole kernels to flour. This gradual grinding generated minimal heat, keeping the flour temperature below 100 degrees Fahrenheit throughout the process. The stones themselves were carefully selected and dressed, their surfaces carved with precise patterns of furrows that channeled grain toward the center while allowing ground flour to escape at the edges. Millers guarded their stone dressing techniques as trade secrets. The best stones came from specific quarries in France. La Ferté-sous-Jouarre produced beurre-stone, a naturally porous quartz that held its sharp surface longer than limestone. A well-maintained millstone could operate for 20 years before needing replacement. Stone milling produced whole grain flour by default. The bran, germ, and endosperm were ground together because medieval technology couldn't easily separate them. This wasn't a nutritional choice, it was a technical limitation that happened to preserve the grain's complete nutritional profile. The bran contains fiber, B vitamins, and minerals. The germ contains essential fats, vitamin E, and additional B vitamins. The endosperm provides mostly carbohydrates and some protein. Together, they create a nutritionally complete food. Separated, the endosperm becomes nutritionally empty calories. The wealthy could afford bolted flour, passed through cloth sieves to remove the coarsest bran particles, producing whiter bread. But even this white flour retained most of the germ and fine bran particles. The cloth sieves, woven from linen or silk, couldn't achieve the fine separation possible with modern milling technology. Analysis of bread residues from medieval London, preserved in archaeological contexts, shows that even high-status white bread contained significant amounts of bran and germ compared to modern refined flour. The Industrial Revolution shattered this system. In 1779, Oliver Evans designed an automated flour mill using bucket elevators, conveyor belts, and hopper boys, mechanical rakes that spread and cooled flour. But the real transformation came with roller mills, introduced in Hungary in the 1830s and perfected in the 1870s. Instead of crushing grain between stones, roller mills used a series of smooth or corrugated steel rollers spinning at high speed, 300 revolutions per minute or more, to gradually shave away the grain's outer layers. This process operates on an entirely different principle. The grain kernel is fractured, and air currents separate the components by weight. The heavy endosperm becomes white flour. The lightweight bran and germ are removed as byproducts, sold as animal feed or health food supplements. The separation is so complete that modern white flour contains virtually none of the original nutrients, except those added back through fortification. The process also generates significant heat, often exceeding 150 degrees Fahrenheit, which oxidizes the grain's natural fats and destroys heat-sensitive vitamins. Roller milling achieved yields of 72 to 75%, meaning 100 pounds of wheat produced 75 pounds of white flour. Stone milling's yield approached 95% because it ground the entire kernel. This seems like an efficiency loss until you consider that the wasted 25% contains most of the grain's nutrition. The roller mill's efficiency was economic, not nutritional. It produced a shelf-stable product that wouldn't spoil because it contained no fats to go rancid. Medieval flour containing the oily germ had to be used within weeks or it would develop off flavors. Modern flour can sit in warehouses for months or years. The speed of adoption was remarkable. By 1900, roller mills had almost completely displaced stone mills in Europe and North America. The driving force wasn't nutrition or taste, but economics and consistency. Roller mills could process grain faster, with less skilled labor, producing uniform flour batch after batch. Bakers could predict exactly how their dough would behave. Consumers could buy white bread that looked the same everywhere, a strange priority that would have baffled medieval bakers who prided themselves on distinctive products. Medieval bread making operated on a timeline that would frustrate any modern commercial baker. The process began not with mixing dough, but with maintaining a sourdough starter, a living culture of wild yeasts and lactic acid bacteria passed down through generations. Bakers reserved a portion of each day's dough to inoculate the next batch, creating biological continuity that sometimes spanned centuries. Records from German bakeries mention starters kept alive for over 200 years, fed daily, traveling with families who emigrated to new cities. The starter wasn't simply yeast for leavening. It was an ecosystem containing dozens of microbial species working in complex symbiosis. Lactobacillus sanfranciscensis, Lactobacillus plantarum, Saccharomyces cerevisiae, and numerous other species each contributed to the bread's flavor, texture, and digestibility. These microorganisms didn't just produce carbon dioxide for rising, they fundamentally transformed the dough's chemistry. When a medieval baker mixed flour, water, salt, and starter, then let the dough rise for 12 to 24 hours, several crucial processes occurred. The lactic acid bacteria produced organic acids, lactic and acetic acid, that lowered the dough's pH from around 6 to approximately 3.8. This acidic environment activated enzymes naturally present in the flour, particularly phytase, which breaks down phytic acid. Phytic acid is the storage form of phosphorus in grain. It's also an anti-nutrient. It binds to minerals like iron, zinc, calcium, and magnesium, preventing their absorption in the human digestive system. When you eat bread made from quick-risen dough with commercial yeast, the phytic acid remains intact, binding to minerals in your meal and reducing their bioavailability. Long-fermented sourdough, however, gives phytase time to break down 60 to 90% of the phytic acid, making the bread's minerals, and the minerals in whatever you eat with it, more accessible to your body. The fermentation process also partially breaks down gluten. The acidic environment and bacterial enzymes don't eliminate gluten, but they modify its structure, breaking some of the long protein chains into shorter peptides. Research at the University of Hohenheim in Germany found that sourdough fermentation reduced gluten content by up to 80% in some flour types. More importantly, it changed the gluten's immunogenic properties, its ability to trigger immune responses. Test subjects with gluten sensitivity tolerated long-fermented sourdough bread while reacting to standard wheat bread made from identical flour. Beyond gluten and phytic acid, fermentation produces compounds that aid digestion. Lactic acid bacteria create exopolysaccharides, complex carbohydrates that slow starch digestion, reducing the bread's glycemic index. They produce antioxidants that aren't present in the original flour. They synthesize B vitamins, actually increasing the bread's nutritional content beyond what the grain provided. Some strains produce compounds that have antimicrobial effects in the human gut, potentially supporting beneficial gut bacteria. Medieval bakers didn't understand biochemistry, but they understood time. Recipes from the 14th and 15th centuries specify fermentation periods in terms of prayers. Let the dough rise while you say 5 paternosters, or leave it overnight while you sleep. These weren't precise measurements, but they ensured adequate fermentation time. The bread that resulted had complex, tangy flavors, dense textures, and exceptional keeping qualities. Sourdough bread stays fresh for days because the organic acids inhibit mold growth and slow staling. Modern commercial bread making operates on a fundamentally different timeline. In 1961, the British Baking Industries Research Association developed the Chorleywood bread process, which reduced bread making time from hours to minutes. The process uses intense mechanical mixing, chemical oxidizers like ascorbic acid, and large doses of commercial yeast to produce bread ready for the oven in under 2 hours from start to finish. No fermentation time means no enzymatic breakdown of phytic acid, no gluten modification, no production of beneficial compounds. The bread rises quickly through carbon dioxide production alone, creating a soft, fluffy texture that bears little resemblance to medieval bread's dense crumb. Even commercial sourdough often isn't truly fermented. Regulations in many countries don't require specific fermentation times or methods to use the sourdough label. Some bakeries add sourdough flavoring, acetic acid, and other compounds to quick-risen dough, creating a product that tastes tangy but lacks the digestive benefits of genuine fermentation. True sourdough requires time, and time costs money in commercial operations where oven space is maximized by rapid turnover. Open a bag of modern commercial bread and read the ingredient list. You'll find 15 to 25 ingredients beyond flour, water, salt, and yeast. These additives aren't accidental. They're carefully engineered solutions to problems created by industrial bread-making processes. Medieval bread contained 3 to 4 ingredients total. The difference reveals how profoundly bread has changed. Dough conditioners, Chemicals like azodicarbonamide, calcium peroxide, and potassium bromate strengthen gluten networks and speed oxidation, processes that occur naturally during long fermentation but need chemical assistance in rapid processing. Azodicarbonamide, the same chemical used to make yoga mats and shoe soles, was banned in Europe in 2005 but remains legal in the United States. It breaks down during baking into semi-carbazide and urethane, compounds with mutagenic properties in laboratory tests. Emulsifiers like mono- and diglycerides, sodium stearoyl lactylate, and polysorbate 60 replace the natural emulsification that occurs during fermentation. They create softer bread that stays fresh longer by interfering with starch retrogradation, the process where bread goes stale. But research at Georgia State University in 2015 found that these emulsifiers alter gut bacteria composition in mice, reducing beneficial species and promoting inflammatory bowel disease. The human gut microbiome responds to the same compounds. Preservatives extend shelf life far beyond what natural fermentation achieves. Calcium propionate prevents mold growth, allowing bread to sit on shelves for weeks. Studies have linked calcium propionate to behavioral problems in children, including irritability and sleep disturbances. The compound doesn't just affect bread, it affects whoever eats it, potentially disrupting cellular metabolism and neurotransmitter function. High fructose corn syrup appears in most commercial breads, ostensibly for browning and moisture retention, but its primary function is palatability, creating mild sweetness that encourages consumption. Medieval bread contained no added sugars beyond what naturally developed during fermentation. The complex carbohydrates in whole grain flour provided sustained energy. Modern bread's added sugars provide quick energy spikes followed by crashes, contributing to the blood sugar instability that drives hunger and overeating. The oxidation issue extends beyond chemical additives. Modern flour is often chemically bleached using chlorine dioxide, benzoyl peroxide, or acetone peroxide. These chemicals whiten the flour and age it, artificially oxidizing the protein molecules to create stronger gluten development. Medieval flour aged naturally, stored for weeks to months, allowing atmospheric oxygen to gradually oxidize the proteins. Chemical bleaching accomplishes in hours what natural aging does in months, but it also creates chemical byproducts that remain in the flour and ultimately in the bread. Bromination, adding potassium bromate to strengthen dough, was standard practice until studies demonstrated its carcinogenic properties. The compound converts to bromide ions in the body, interfering with iodine metabolism and potentially disrupting thyroid function. It's now banned in most developed countries except the United States, where it remains legal but less commonly used. Medieval bakers never needed it because their slower processes and whole grain flour naturally developed strong dough. The most insidious additives may be the enzymes. Modern bread contains fungal alpha amylase, xylanase, lipase, and other industrial enzymes added to improve dough handling, increase loaf volume, and extend shelf life. These enzymes break down starches and proteins during mixing and baking, creating effects similar to, but faster than, natural fermentation. Unlike chemical additives, enzymes are classified as processing aids in many jurisdictions, meaning they don't require labeling. A consumer reading flour, water, yeast, salt on an ingredient list may be eating bread containing a dozen unlabeled enzymes. Research at the National Institute for Public Health in the Netherlands found that baker's asthma, an occupational disease affecting up to 30% of commercial bakers, is primarily triggered by fungal alpha amylase. Workers inhale the enzyme dust and develop severe respiratory allergies. The question rarely asked is, if inhaling these enzymes causes immune reactions, what happens when you eat them? The enzymes are denatured during baking, but they've already modified the bread's molecular structure, creating protein fragments and starches that don't exist in naturally fermented bread. Medieval humans had digestive systems identical to ours. Their intestines were the same length, their stomach acid the same pH, their digestive enzymes the same chemical structures. Yet they processed bread fundamentally differently than we do, not because of biological differences, but because of what the bread contained and how it was prepared. The human digestive system evolved to handle whole grains, but it requires help. Our saliva contains amylase, which begins breaking down starches in the mouth. Our stomach acid denatures some proteins. Our small intestine produces enzymes that break down carbohydrates and proteins into absorbable molecules. But we lack the enzymes to break down certain grain components, particularly the complex carbohydrates in bran and the phytic acid that binds minerals. This is where fermentation becomes crucial. Medieval sourdough fermentation essentially pre-digests bread. The bacteria and yeasts in the starter perform chemical transformations that our digestive systems cannot. They break down complex starches into simpler sugars. They produce enzymes that dismantle phytic acid. They modify gluten proteins into shorter chains more easily processed by human enzymes. When medieval bread entered the digestive system, much of the hard work was already done. Modern bread enters your stomach essentially raw at the molecular level. The starches are complex and largely unmodified. The proteins are long chains that require extensive enzymatic breakdown. The phytic acid is intact, ready to bind minerals. Your digestive system must do all the work that fermentation once accomplished. For some people, this works adequately, though inefficiently. For others, it triggers problems. The glycemic impact differs dramatically. Medieval whole-grain sourdough bread had a glycemic index around 45 to 55, comparable to oatmeal or beans. Modern white bread scores 70 to 85, comparable to pure glucose. This means modern bread spikes blood sugar rapidly, triggering insulin release, followed by a crash that stimulates hunger and stress hormones. Eaten repeatedly, this pattern contributes to insulin resistance and type 2 diabetes. The fiber in medieval bread slowed sugar absorption. The organic acids from fermentation further blunted the glycemic response. Modern bread, stripped of fiber and quickly fermented, hits your bloodstream like liquid sugar. The gut microbiome, the trillions of bacteria living in your intestines, responds differently to different breads. Research at the Weizmann Institute in Israel found that people's gut bacteria composition determined whether they responded better to sourdough or industrial bread. But crucially, the sourdough promoted more diverse bacterial populations and higher levels of beneficial species like lactobacillus. Industrial bread promoted less diversity and sometimes increased populations of species associated with inflammation. Gluten sensitivity, distinct from celiac disease, affects millions who don't have the autoimmune markers for celiac. Many of these individuals tolerate long-fermented sourdough while reacting to standard bread. The mechanism isn't fully understood, but research suggests that modern bread's rapid fermentation leaves more intact gluten epitopes, specific protein sequences that trigger immune responses. Long fermentation breaks these sequences down, reducing immunogenicity without eliminating gluten entirely. The inflammatory response to modern bread may also involve the additives, not just the grain. The emulsifiers, preservatives, and enzyme residues all interact with intestinal cells in ways that natural bread does not. These compounds can increase intestinal permeability, leaky gut, allowing partially digested proteins to enter the bloodstream and trigger immune responses. Medieval bread free of these additives didn't create this vulnerability. Perhaps most significantly, medieval bread was eaten as part of diverse diets that included far more fermented foods than modern diets. Cheese, preserved vegetables, beer, and wine all contributed beneficial bacteria to the gut microbiome. This robust microbiome could better handle the digestive challenges of bread. Modern diets, often lacking fermented foods and high in antibiotics and antimicrobial compounds, create impoverished gut microbiomes less capable of processing any grain products efficiently. Medieval bread's characteristics weren't primarily driven by health knowledge. They resulted from economic and technological constraints that happened to produce healthier bread. Fresh bread was expensive. Fuel for baking ovens cost money. Wheat cultivation required labor. These factors shaped bread making in ways that modern industrial economics has inverted. A medieval household baked once or twice weekly, producing enough bread to last several days. This schedule demanded bread that stayed edible, resistant to mold and staling. Sourdough fermentation provided exactly these qualities without any additives. The organic acids inhibited mold. The complex flavor development meant bread that tasted better on day 3 than industrial bread tastes on day 1. Economic necessity drove practices that created superior nutrition. The class distinctions in medieval bread reveal interesting patterns. The wealthy ate white bread, considered more refined and desirable. The poor ate dark bread made from rye, barley, or mixed grains with all their bran intact. Medical texts of the period claimed white bread was more digestible and healthier. Modern nutritional science reverses this entirely. The peasants' dark whole-grain bread provided far better nutrition, more fiber, more vitamins, more minerals. The aristocrats' refined white bread, while still containing more nutrients than modern white bread, was nutritionally inferior. Status and health diverged. Millers controlled crucial infrastructure, the mills themselves, and charged tolls for grinding grain. Households couldn't easily mill flour at home because the equipment was too expensive and labor-intensive. This monopoly actually preserved quality because millers, as specialized craftsmen, maintained their stones carefully and developed real expertise. When cheap home grain grinders became available in the 19th century, quality initially declined as people used poorly maintained equipment. The economic concentration of milling in medieval guilds maintained standards that competitive markets initially undermined. Modern bread economics operate on entirely opposite principles. Bread must be cheap because it's a staple food. Cheap bread requires high-speed production, which requires additives to compensate for eliminated fermentation time. Shelf life must be long because distribution chains are extensive. Long shelf life requires preservatives and removal of anything that might spoil, like the nutritious germ with its perishable fats. The economic optimization for cheapness and convenience systematically removes everything that made medieval bread healthy. The true cost difference is hidden. Medieval bread was expensive in immediate cash, but cheap in health consequences. Modern bread is cheap to purchase, but expensive in its contribution to chronic diseases. A loaf of industrial white bread might cost $2. A loaf of genuine long-fermented sourdough from whole-grain flour might cost $8. But the health costs of eating industrial bread daily, increased diabetes risk, nutrient deficiencies, digestive problems, dwarf the $4 price difference. We've optimized for the wrong variable. Across Europe and North America, small bakeries are reviving pre-industrial techniques. They're not recreating medieval bread exactly. Modern ovens and temperature control provide real advantages, but they're recovering the essential principles: whole grains, long fermentation, minimal additives. These bakeries often charge premium prices, creating a troubling dynamic where healthy bread becomes a luxury good unavailable to people who need it most. Some individuals have taken bread making into their own hands, maintaining sourdough starters and baking at home. The practice has grown exponentially. Searches for sourdough starter increased by 400% during the COVID-19 pandemic. Home bakers report that bread they previously couldn't tolerate becomes digestible when they make it themselves with long fermentation. The anecdotal evidence aligns with biochemical research. Time and microorganisms matter more than ingredients lists might suggest. Agricultural researchers are working to revive ancient wheat varieties. Einkorn, emmer, and spelt, once dismissed as primitive, are being cultivated again by specialty farmers. These grains command higher prices, but offer nutritional profiles and digestibility that modern wheat cannot match. The challenge is scale. Modern agriculture is optimized for high-yield dwarf wheat. Converting fields to ancient varieties requires accepting lower yields and finding markets willing to pay accordingly. The most promising developments may come from understanding, rather than simply recreating the past. Scientists studying medieval bread aren't trying to return to medieval technology wholesale. They're identifying which specific practices mattered for nutrition and digestibility, then implementing those practices with modern precision. Controlled fermentation at specific temperatures and pH levels. Measured enzyme activity. Documented microbial populations. This isn't nostalgia. It's applied biochemistry informed by historical practice. But individual solutions cannot address systemic problems. As long as industrial bread remains cheaper and more convenient than nutritious alternatives, most people will eat industrial bread. Meaningful change requires either regulatory intervention, standards for fermentation time, restrictions on additives, labeling requirements for processing methods, or economic shifts that make real bread affordable. Neither seems imminent in market economies, where food price is the primary competitive variable. The transformation of bread from medieval health food to modern nutritional problem wasn't a single change but a cascade of modifications, each seemingly rational in isolation, that cumulatively destroyed bread's fundamental character. Higher-yielding wheat varieties, faster milling processes, reduced fermentation time, chemical additives. Each change solved specific problems, feeding more people, reducing costs, extending shelf life, while creating new problems that took decades to manifest in population health statistics. Medieval bakers didn't make superior bread because they understood nutrition science or biochemistry. They made superior bread because their economic constraints, technological limitations, and craft traditions happened to align with human digestive physiology. Slow stone milling preserved nutrients. Long fermentation broke down anti-nutrients and modified gluten. Whole grain flour provided complete nutrition. These weren't deliberate choices toward health. They were the default outcomes of available technology and established practice. The lesson isn't that we should abandon modern technology and return to medieval methods entirely. It's that we should question the assumption that newer is automatically better. The industrial optimizations that make modern bread cheap and uniform have made it less nutritious and less digestible. We've solved problems that didn't need solving. Bread doesn't need to stay fresh for weeks. It needs to nourish people who eat it. We've created problems that didn't previously exist. Widespread gluten sensitivity, blood sugar instability from refined carbohydrates, gut dysbiosis from emulsifiers and preservatives. Bread can be medicine, or it can be empty calories laced with industrial chemicals. The grain hasn't changed. The human digestive system hasn't changed. What has changed is everything we do to grain before it becomes bread. Medieval bakers, working with simple tools and inherited knowledge, created food that sustained civilizations for centuries. Modern industrial bakers, working with sophisticated equipment and chemical engineering, have created a product that increasing numbers of people cannot safely eat. Understanding why this happened is the first step toward bread that nourishes rather than harms. The biochemical principles that made medieval bread healthy aren't mysterious or lost. They're just slow, careful, and incompatible with industrial efficiency. That's not an argument for inefficiency. It's an argument for redefining efficiency to include the health of people who eat the bread, not just the profit margins of companies that sell it.